Hello, I'm Alexis Ravenscroft, a sophomore chemistry major here at WVU. I do my research under Dr. Pop, and I'm presenting my poster on my studies of organic transformations using operando spectroscopy and computational chemistry. When I first began my research in the spring, I was studying IR spectroscopy and using it to analyze the esterification reaction of limited acetic anhydride and excess methanol catalyzed by sulfuric acid. I began by learning how to operate the machine, and then I learned how to use the software. Methanol and acetic anhydride were added together into a vial because they could not react without the catalyst, due to the acetic anhydride having to be protonated, as seen in the figure. Then variable amounts of the catalyst were added. The machine tracked the reaction by producing a three-dimensional graph as seen in the top right corner of the first dataset. This is a collection of the 2D IR spectra every 30 seconds over an hour. The IR spectra uses light to analyze the unique bond-specific vibrational stretching, so the reader can see what kind of bonds exist within the molecular structure. It can be seen in this picture that the peaks shift. This shift indicates the reaction has proceeded because as the reactant decreases, the product increases. When all of the limiting reactant spectra is gone, the reaction has gone to completion. When the reaction completes, the sulfuric acid reforms and has no effect on the products or reactants any further. We were able to gather the data on how fast a reaction proceeded to completion and compare it to the varied amounts of catalyst. This was done by analyzing the decreasing speed of one wave number, which is the frequency a bond appears at, and the increasing speed of another. This can be seen in the fifth graph where the increasing rate and decreasing rate at the different spectra align. In the first four graphs, they are a height of peak versus time graph. It can be seen that the rate is originally linear. And if zoomed into the first 200 seconds, it would appear completely linear, showing that the catalyst is affecting the reaction at a constant rate. The final graph is the kinetics observed versus the concentration of the catalyst, which appears to be linear. Therefore, we concluded that the sulfuric acid has a kinetic first rate law and affects the reaction directly. This fall semester, as we transitioned to online learning, so did my research. We transitioned to computational chemistry, which is the use of computers to do experiments on digital models of molecules. The benefit of using computational chemistry is the ability to test and observe a single molecule rather than a sample of molecules. It uses theoretical chemistry in these observations so that they follow all known rules of chemistry and provide accurate, precise data. This project was an extension of the Wong group's research, where they were analyzing a macrocycle of 2,2,7-dibromophenanthrene, or DBPhen for short, and with two dibenzylamine linkages. Using proton NMR spectroscopy, they found that at room temperature, the structure had one stable conformation where the two sides of the macrocycle had defined planes. When the temperature increased up to 90 degrees Celsius, the structure was able to interconvert between the two planes, suggesting a transition state for the macrocycle. This is seen in the NMR spectroscopy data in the first figure shown. When looking at the peaks above 7, which are arene protons, and the peaks around 4, both encircled in blue, the peaks lose the thin, well-defined nature, as the temperature increases to become a larger wave, circled in red, which shows that the originally two well-defined cyclic structures are now merging together, indicating free interconversion between the two planes. We use Spartan to analyze different conformers, which are stable energy-varied formations for the macrocycle. And analyzing the energies, we found that our most stable structure agreed with the data collected by the Wong group. We then began to use the structure to modify the dihedral angle between the amine and the adjacent ring to flip the structure to the other side of the DBPhens. In the second figure, it begins with the groups pointing out of the screen, then symmetrically to the side, then to the back, which is the complete system for the transition. The transition state is a peak of energy where the molecule is able to shift between the next state and the prior state. We found the intermediate states, which are the saddle point between the two transition states and help the transition along. In the end, it took many trials to find the energy formations we were looking for, and they showed the intermediates, showing that if provided with enough energy, the structure could proceed by interconverting between the two planes, which can be seen in figure 3. In this data set, we found that our data for the intermediates were also consistent with what was predicted. Overall, these past 2 semesters have taught me a lot about mechanisms that reactions and molecules go through, and taught me how to use different software to benefit the chemical research that I wish to do. I am excited to continue on with research, and I'm very grateful to my mentor, Dr. Pop, for letting me into his group and helping me learn throughout this journey.